having seen the progression of storage technology, and now, with lithium in the spotlight and the majority of the market being lithium, it's been really interesting to see all the different ways people are applying those technologies and how they're all looking at them. Being an independent design engineering firm at SepiSolar, we are putting plans and communicating these systems to regulators, of course, utilities and permitting authorities, but also asset managers and developers, EPCs, working with OEMs. There's a whole ecosystem of stakeholders that all have to work together, and all these requirements and objectives and goals that everybody is very interested in, like economics, like safety, code compliance, all that, all has to come together at the end of the day and work. And it's not as straightforward as you might think. There's a lot of nuances, and I'm really happy to be here with Matt Harper and of Avalon Battery, because one of the things that I think lithium providers have done, and now we're seeing other providers like flow battery providers like Avalon Battery and flywheels and advanced lead and other types of technologies, are giving us new ways to approach those same systems. And these technologies have benefits, and they are sometimes very nuanced. And at a high level, in the media, there's a lot of details that can get breezed over. But coming from a company like SepiSolar, it's our job to dig into the details, to surface those details, and make sure that these projects meet all the project requirements that they need to meet to make everything work and make everybody happy. So super excited to answer your questions, but would like to introduce Matt Harper of Avalon. So Matt, who are you and what's your company?
It doesn't sound like you introducing me. That sounds like me introducing me. So I'm Matt Harper, Chief Product Officer and one of the co-founders at Avalon Battery. Let me introduce myself first. So I've been doing renewable energy technology development for about 25 years. I started off my career in the fuel cell industry, pulling a wrench in the world's first fleet of fuel cell buses, and spent about 10 years in fuel cells, and then and also the sort of hydrogen refueling space. And then in 2005, went to work for a company called BRB Power Systems, which is the original licensee of the flow battery technology into North America, and have essentially been working on the vanadium flow battery technology ever since. Myself and my co-founders spun Avalon out of our last company about 5 years ago, and over the last 5 years, we've been developing products that we believe bring the fundamental advantages of vanadium flow to large distributed scale and small utility scale projects, especially ones related to renewable energy generation through solar and wind. To talk a little bit about the company and the technology, which I think is something I should also do, I guess.
Yeah.
So the fundamental point of the vanadium flow technology is that it's a battery chemistry that does not degrade at all based on cycle life. So you can run these batteries through tens of thousands of deep discharge cycles without any perceptible degradation. The way we achieve that is that in a flow battery like ours, all of the charge and discharge reaction takes place entirely in a liquid phase. The electrodes and a lot of the other electroreactive components that are part and parcel of most batteries aren't actually playing an active part in the charge and discharge and energy storage part of the reaction. And what that means is that because the energy storage itself is happening in a liquid, it remains in that liquid over time. We can manage that liquid very effectively, and so over decades and over tens of thousands of cycles, you're not seeing any degradation in the overall performance. I think that's it. Anything else? What did I miss?
That's great.
Yeah. Okay. Good. Great. So we sell actually sort of commercial. So we sell most of our projects into commercial and industrial applications for customers who want to manage demand charges or self-generating energy through renewable power and want to make the most effective use of that self-generated power, or sort of the distributed or utility scale generation where people want to generate that electricity most effectively, store it, and then repurpose it onto the grid at a time that's most economically valuable.
Excellent. Excellent.
So we just want to make sure that there's no technology problems coming from the web, because we did want this to be interactive all over. So just let's. I just want to make sure over here. That's off. Is your video on? Yes. So your video is on. Everything else. All right.
Should we get into it?
Let's get into the questions from the audience here, and I'll just make sure that people on the web. Is your sound boosted as much as possible?
Yes.
Okay. All right. There we go. Okay. Let's start the first question here.
So this is an Ask Me Anything series. So we just recently started this a month ago. So anybody who, as it sounds, ask us anything. Ask the hard questions. There are no stupid questions. It is supposed to be technology focused. If you have questions about lithium technologies and the different flavors of them, there are several: titanate, nickel manganese cobalt, nickel cobalt aluminum, iron phosphates. If you want to know how they're packaged or manufactured, risks, benefits, costs, degradation, round trip efficiency, auxiliary loads, use cases, demand reduction, time of use arbitrage, infrastructure deferral availability, anything at all, feel free to have at it. We have seen a lot of different kinds of batteries, you know, and would love to answer questions.
What he said. Okay. Hi. Yeah.
And for those of you on the phone, we'll repeat the question so you can hear.
Yeah, all kinds of drugs. I want to ask you, one of the important features that come up recently is integrating EV technology with storage technology. So I will ask you, what's the idea that John, who is one of the specific examples of a project in which you have integrated from any exposure with EV with.
Okay. So the question was, please give a concrete example of a project that has integrated electric vehicles, that's the key component here, with solar and storage in some kind of a project or a use case. And I would love to answer that question.
Okay. Yeah, sure. Have you actually, so it was a very specific question in that you were actually asking about where, you know, a specific example of where that's been done. We haven't done that. We're in the middle of deploying something into an application like that. But Sure. Okay. Yeah. Perfect. Well, let me jump into it. So the application that I think is going to really dominate in electric vehicles is that plugging a whole lot of electric vehicles into the existing automotive infrastructure is going to overload the electric grid. Right? If you think about fueling stations where people are going to, you know, drive up and plug in their cars to you know, supercharge over 5-10 minutes while they grab a cup of coffee in the morning, or the kind of parking lots where people are going to go and park their cars for the day or overnight, or while they pick their families up at the airport, what have you. All of those applications require far more power flowing into a single space than the grid is currently built out for. And if you think about the cost of installing additional electric infrastructure into a lot of those locations, you know, think about, you know, a parking garage in downtown New York City. You're not going to be able to upgrade the electric infrastructure to support that. Think about a fueling station, you know, in the middle of the desert that's hundreds of miles from everywhere, where everyone is stopping to refuel their vehicles. You're not going to be able to expand the infrastructure significantly. So, you know, the basic concept is, you know, can you take a battery and regulate the amount of power flow into those particular locations? And, you know, we think that, you know, you absolutely can. We've done a lot of modeling on, in particular, airport applications, because what's interesting about those is that you can't do any time-based arbitrage, right? People are driving to an airport, stopping, they're going to be there for an hour to an hour and a half, picking up their family, dropping off their family, whatever they're doing, so they've got a very short window in order to do that charging. That creates a very difficult problem, because you can't average out that load over the course of the day. So for applications like that, I think that there's going to be a huge amount of batteries that end up being deployed as the number of EVs on the road start to increase.
And I'd like, if I can, there's a very specific project that SepiSolar worked on that exactly lines up with your question and what Matt just said, which is this was at an Avis rental car facility in New York City, right next to LaGuardia Airport. There was a 600 amp main service, 208 or 480, don't remember the voltage, But this Avis rental car wanted to convert their cars to electric. They wanted to be, you know, the electric rental car of the future, and they wanted people to rent electric vehicles. So they wanted to install a bunch of level 2 and level 3 EV chargers. But there was a problem. Where they wanted to install these EV chargers, where the parking lot was, there was like a, I forget it, like a 4-gauge or a 2-gauge conductor fed by a breaker in the main to a sub-panel that would power all these EV chargers, and that sucker was maxed out. There was no capacity, no electrical capacity to run these EV chargers, or you'd be blowing the breaker in the main over and over again. So what we did is actually kind of, it's a microcosm of what's happening right now on the grid with what I would call infrastructure deferral, which is instead of ripping up that tiny itty-bitty little 4-gauge or 2-gauge conductor that ran about 300 feet, instead of ripping up the concrete in New York City next to an airport, you know, talk about, I mean, we were looking at hundreds of thousands of dollars of labor, union labor costs and permitting costs. Instead of spending that kind of money, it was cheaper and better for the customer to install a storage system with a solar system right next to the EV chargers, because you can put those assets almost anywhere, right? If you got some roof space, you got some parking lot, you can drop that equipment right next to where it's needed the most. And so we were able to provide all the energy those EV chargers needed by, in essence, trickle charging, limited by that 4-gauge conductor from the grid, storing it into the battery overnight whenever possible, and then the EV chargers would feed from the battery and drain the battery down. And so and then there was some solar there as well. So you always had availability for the EV chargers from solar and storage. You did not rely on the grid. That made Con Ed happy. It was cheaper for the customer, and the customer was able to achieve all the goals they wanted. No ripping up concrete, no replacing copper.
Increase the broader project. Even last year, something that you or my friends or somebody else. We have these projects to look at. You can see what working to get information about the few mentioned.
Yeah. See me afterwards. I'll give you my card. We'll share information. Yeah. Lots of details.
Does anybody, right now we don't have anybody questions from the web. Does anybody have any questions from the web that wants to answer? Please press *6 if you want to ask a question from the web. Meanwhile, we'll take one more question from the audience.
Or, if there's no questions from the audience, I've got a question. Why, I mean, so there's a lot of flow batteries, right? I mean, we're seeing all kinds, zinc bromide, zinc iron, zinc bro. There's, like, what is so special about, like, why vanadium, I guess?
Sure, okay, great question. So the reason why is that it is the most stable flow battery chemistry out there. And you know, the promise of flow batteries is that they can offer this very, very deep discharge over many, many years without the kind of degradation you see in the conventional battery. But what you get is a lot of different kinds of degradation modes that exist inside inside a lot of different flow batteries. Things like unintended side reactions that lead to hydrogen generation. Things like crossover of different materials from the positive to the negative couple. Things like in so-called hybrid flow batteries where you've got a liquid couple with a metal couple as well. You do get degradations based on electrode reactions, and you do need to do some maintenance on those electrodes from time to time. In the vanadium system, we don't have that at all. The battery has been fundamentally proven by independent third-party engineers to last decades in the field. There's been over 100 megawatt hours of this technology type installed over the last 15 years at scale in the field. And it's that, that experience and that amount of scale that allows us to prove that it really does have the longevity that we claim it does.
So you've built vanadium flow battery systems in the field that have lasted longer than 10 years, and you've seen no degradation. And has anybody third party approved this?
Yeah. We had on our current generation of product, we had DNVGL come in and do a bankability assessment on the technology itself. They looked at both a sort of one of our beta units we delivered to the field about 2.5 years ago, and then one of our sort of current commercial generation units as well. They didn't look at just one of the current generation. They looked at a whole fleet of about 30 units that were coming off the line in our factory, and they essentially validated exactly what we're saying, which is that through 10 years or more of charge and discharge cycling, they were not able to measure any degradation in the battery performance.
Wow.
I think one of the things that really helped us in that evaluation, which is really critical to think about, is that the way flow batteries in general have frequently been built as very large sort of highly engineered projects, where a lot of the components of the system are actually being installed not at the factory, but rather in the field. And we think that that's a terrible way of A, keeping costs down, and B, making sure that you've got really good quality control over the product itself. What Avalon has done is that we took the fundamentals of the vanadium flow technology and turned it into a totally turnkey unit that ships from the factory 100% complete. And what that means is that we do 100% testing of these things before they leave the factory. We have an identical side-by-side data set of every unit that we've ever shipped, and that's a data set that is unparalleled in the flow battery industry. There's no one else that has anywhere near that level of data on exactly how these things perform and exactly how they behave and exactly how they should be expected to work once they land in the field. That gives us a huge advantage in terms of optimizing the performance of these things over time and really making sure that the product that we deliver into the field is going to meet the intended specifications.
Okay, so like your battery will ship wet, full of the electrolyte,
Yep.
and fully integrated with AC 480 volts or something.
That's correct. Yeah.
Coming out?
So it's not just the battery or the stack of batteries. It's the entire battery system that goes around that. We include the cooling. We include the battery management system. We include secondary containment. Literally, all you need to do with this product is put it onto a concrete pad or similar support, connect the electrical connections, and let it run.
So like at SepiSolar, we design a lot of lithium systems and lead acid, and one of the things like with lithium systems is, and the CNI level, you can't, the packs aren't necessarily rated by Department of Transportation for shipping. So the manufacturer, and if you do ship them, you void warranty. So you have to ship the packs separately from the enclosures, and you have to do some integration and terminations in the field. You're saying you don't have to do that kind of stuff?
We don't have to do that. The turnkey battery system, the UL 1973 rated full turnkey package is shipped 100% fully complete from our site. It is fully functional on the truck when it arrives. The installation process includes dropping it down and connecting wires. That's it.
Okay. So do we have questions from the audience?
We've got questions. Okay. We want to. So our first question is a very basic one. James, if you have a grid tie inverter install, how do you integrate a battery? So that's kind of a very general one. No specific battery technology about that. Do you want to just give an overall design answer?
Sure. So the question is, if you have a grid-tied inverter already installed, like there's an existing solar system, how would you integrate a battery into that, perhaps aftermarket? If that's the question, there are some products actually that I know are being developed and commercially available today where you can retrofit an existing solar system with batteries. I mean, maybe a brute force, dumb, simple, easy way to do it would be AC coupling, right? In an AC coupled solar plus storage system, both the solar and the storage system have separate inverters. They're essentially completely separate systems that just happen to interconnect with each other on the AC side. This is very common. In my opinion, it's actually kind of a problem. It makes these solar plus storage systems a little more expensive and less efficient than they need to be. You have two inverters. There's more losses when you're charging the storage from the solar because it's going through two inverters now and then back out. It actually has 3 passes. Anyway, so that is a flexible, convenient way, perhaps, to integrate a battery into an existing solar system. And more recently, actually, just literally within the past couple of months, SepiSolar, we've been turned on to products provided by suppliers. I'll think of their names, EIQ, and there are some others where you can actually do that exact same integration, but in a DC coupled configuration. So companies like EIQ have a product called Easy Store where you can almost like splice into the circuit between the solar panels and its existing inverter, and you can run that circuit to a battery And with some sophisticated controls and conversion, you can make that battery appear like any other solar system to the inverter. And effectively, you don't have to screw up the operation of the solar. You don't have to mess with anything that's already there. You just get all the benefits of DC coupled storage added onto it. So there's a couple ways to do it, and it's definitely a solved problem at this point.
And I think one of the things that I would add to that is you typically don't need to mess around with your interconnection agreement. So one of the problems about adding batteries onto solar is that frequently you'll have to go back and redo your interconnection. If you're not changing the configuration of the inverter itself, not adding more power conversion on the AC side, most regulations will allow you to add that on without actually reopening that interconnection question. And that's very, very critical to people who are operating, merchant solar plants that have been interconnected under PPAs that are maybe a couple of years old, where the payment rates are very, very beneficial on those, and they do not want to revisit the question of what those PPA rates are. So that DC coupling allows you to add the battery capability in without revisiting that whole sort of contractual interconnection question.
Great.
I would just add to Josh's point. We're big believers in DC coupling as well. One of our major commercial partnerships is with a company called Nextracker, world's largest manufacturer of tracking systems. We've done a very deep integration with Nextracker over the last couple of years to make sure that the solar and the batteries are combined into a single inverter on the DC bus. That saves a whole ton of energy in terms of round-trip efficiency. It also saves a whole lot of cost in terms of individual inverter boxes and all of the electrical infrastructure that has to go around that project overall. Yeah.
Let's move on to one more question from the web, and this is kind of a follow-up for the Avalon flow battery, and that is the HVAC requirements for flow batteries. And so let's talk about Avalon, but also other flow battery systems that may have any HVAC requirements.
Sure. So I'm trying to think about how to separate those two things out. So fundamentally, flow batteries like to operate at higher temperature than lithium-ion cells do. Right? Think about lithium-ion cells. You're typically starting to eat into your warranty drawdown. Anytime you have your temperatures, ambient temperatures going above about 23 or 25 degrees C, and it gets much worse as you sort of go higher than that. That means that typically those need to be either air-cooled or often have an HVAC system installed in order to keep those batteries within that operating range. We don't have that problem primarily because our batteries like to operate at higher temperature. Our efficiency and energy storage capacity goes up as the temperature increases. We usually like to operate our batteries at about 40 degrees C, or what's that? My Canadianness is showing. It's about 105 Fahrenheit, right? Yeah. So what that means is that in most situations there's no need for any additional cooling, and where there is a need for additional cooling, we can do that. I'm thinking about sort of installations in the Central Valley or something like that, where you've got temperatures the 115, 120, 125 range. We can do that simply by virtue of air cooling the system. So, you take away, the added parasitic losses, the added O&M expense, and the added capex of having, an HVAC system either on your container or however you're going to do it on the lithium side, and you just have a simple air cooling system in our configuration. That's not the way that all flow battery companies do it. I can't comment on all of them, but I would say that usually when I've looked at a lot of these big sort of containerized flow battery systems, usually there is some form of active cooling installed, whether it's a chiller connected through a liquid-to-liquid heat exchanger or something like that. We just found that was a very, very expensive way of doing it. And so what we've developed is a way of directly cooling our batteries simply from ambient air.
Josh, do you have anything to add to that?
The only thing, that was a good response. I mean, the only thing I would add to that, I guess, is I've always, from a warranty compliance perspective at SepiSolar, whenever we design lithium systems, I mean, we're always double-checking the HVAC system, because I almost think of HVAC as warranty insurance. If the HVAC goes down, those batteries shouldn't be operating, because the whole system really needs to go down. It's sort of like a single point of failure kind of a situation. If the HVAC breaks, the whole system needs to stop, or else you can literally have a thermal event. So safety has to be really critical in all those kinds of systems, and you have to keep a close eye on it. It's nice to hear that you don't have quite as complicated of a thermal management system, and if it were to break, it's not catastrophic to the system. That would actually make designs a lot simpler.
Well, the other thing that I talk about is, if you think about cooling loads, say you're operating out in the Central Valley at 110 degrees, right? If you're trying to keep your batteries at 70, you've got a pretty big parasitic load that accrues to actually making that temperature differential happen. Whereas if we're able to let our batteries float at about 105, the difference, the difference between those two temperatures is very, very narrow. That means that our, the parasitic loss that accrues to that cooling load is much, much smaller.
So yeah, I mean that's one of the slams against flow batteries that I hear often is they're not as efficient as lithium batteries. Are you saying then that part of the way that flow batteries make up that gap is with far less auxiliary load because of the HVAC? That's
absolutely true. I recently visited one of the biggest lithium installs in the U.S. Down in Imperial Valley, just east of San Diego. And I think it was a 20 megawatt system or something like that. And you sort of see this building that is, you walk inside, it's like a refrigerator, like walking into a refrigerator, because it's a whole room full of buildings that are full of batteries that need to be kept at 70 degrees C. Outside the building, though, what was most amazing is that you'd see these racks of inverters, but next to the inverters, even bigger than that, were the cooling systems. Right, because you've got a massive, massive load that accrues to try to keep these batteries in the normal operating range. So it is a huge parasitic load, and it's one of the things that's not often considered when you're thinking about the overall sort of system level efficiency of these projects.
So it's not just the auxiliary load round trip efficiency issue; it's also a footprint issue. I mean, that's another slam I hear about flow batteries is they're big, and it sounds like you're saying there's actually a lot of footprint people need to allocate for the chillers, which I'm sure, when we were designing these systems, you have to take all that into account.
No, that's absolutely true. I mean, a lot of my experience in this industry was related to, not taking these technologies and deploying them out in the field, doing the kind of customer side installation. And what we found is that there's so much extra stuff that you have to add on at a system level in order to make a lot of these things happen. What we really tried to do as Avalon was to take all that stuff and put it sort of inside the box, so that there's no additional work that you need to do, and so that you can optimize the way those things work together, within the sort of core product.
Got it.
Yeah.
Okay. Let's take some questions from the audience. Please go up to the mic and ask again. Anybody? And if you are listening in on your phone, dial *6, and we can get you on live. Again, dial *6. And if you're also on the web, you can do it through the chat channel, which people are doing also.
The efficiency up to cold temperature, what temperature would that have?
Yeah,
repeat the question.
Sure. The question is, does the efficiency level change at cold temperatures as well? The answer is it depends. If the battery is being used regularly, it will self-regulate and generate its own heat. If you were to have one of these batteries that was sort of not performing for some extended period of time and the temperature were to drop down, the first couple of cycles would be at a lower efficiency, but it would build back up over time.
Can you quantify that at all? Like, would it be a
you're probably going to see a 15% drop in overall capacity over the operating range. So if it's a 100 megawatt hour array, you're going to be down to 80 megawatt hours until it comes back up to temperature. Yeah. But again, in normal operation, the temperature is self-regulating. We set it to be between 90 and 105 degrees all the time. So long as you're regularly exercising the battery, it's not going to get out of that range. Okay.
All right. Next question. You're an ask.
Next question.
Yeah. Ask SepiSolar anything.
Go ahead. Yeah.
Go ahead.
A couple of simple questions. Really difficult, concrete answers. I have a 6 kilowatt PV system, 2 cells, 2 inverters, 2 inverters, and each of the inverters and they have a output. Without the PV, on the PV, very big, output enough. Give me an example of what is a simple battery confidence of the math with everything. Do the battery.
So So the question is, you've got an existing PV array that uses SMA inverters, 2 strings, total of 6 kilowatts. So we don't currently. The product that we build right now is optimized for sort of commercial, industrial, and larger. So we don't build anything at that scale. However, we have in the past worked with the SMA products. I know that they do have certain battery types that are natively integrated into their platform, and it's just a question of finding the right battery. Yeah.
What is the extra circuitry that is needed? This is a very simple question. Like really you need some extra circuitry. Like really manual or semi-automated. What circuitry do you have?
The question is what circuitry and additional components would you need? Likely some wires, some conduits, some breakers, maybe a transfer switch if we're going off grid, or if it's grid connected, perhaps a breaker into the main, and maybe a sub panel for additional loads. Yeah, I mean yeah, and depending whether we do DC coupled or AC coupled, it changes too. Depending on what the use case is, it'll change a little bit. Like, is it for backup or is it for self-consumption of the PV or something else? So yeah. Yeah, let's dive into the details more afterwards. There's a lot of design work behind that we can do too.
Yeah. Sure. Again, we've got a.
I need a whiteboard. Draw it out.
We've got another question from Paul. Best power applications for flow batteries, e.g. load following spinning reserves, longer-term microgrid formulation. Where are flow batteries perhaps not the best choice, e.g. frequency regulation, voltage, or variable support, or variable support?
Yeah.
Yeah.
Sure, I can take that. So it is definitely true that flow batteries are typically more useful in applications where you've got longer duration discharges. So, not sort of the, seconds to minutes to, to 15 minutes that you would see in some of the ancillary services applications and some of the power quality stuff you're talking about, but, the longer duration capacities. Where we do see that it makes a lot of sense to use these batteries for some of those applications is in situations where you have very, very high cycle counts. So if you're doing some of those, shorter duration regulation type applications, but doing it 10, 15, 20 times a day, you can very quickly get to a very, very large number of charge and discharge cycles. And at that point, it, really does make sense to have a technology like ours. The other thing that I would say is that, there's this big conversation, and we didn't get the storage bingo cards, the storage buzzword bingo cards, but there's this whole conversation going on right now about application stacking or value stacking. The concept there is, there are, dozens of different ways that batteries can actually add value to the grid or the grid connected installations. And the concept is that, you can take a lot of these different use cases and kind of stack them on one another and dispatch them into the market depending on what happens to be most effective or most valuable at a particular time. In those kind of applications, it would make sense to have a flow battery because you can do both things at once. You can do both the longer term, the longer term dispatch, the sort of bulk power shifting and energy management, as well as some of those shorter duration applications at the same time.
Got it. So like demand charge reduction, things like that, the flow battery could. So just in the spirit of concrete examples, I think there's a concrete example of that SepiSolar designed a system. I think using your battery, where the grid was limited to like 750 kilowatts AC for whatever reason. The utility couldn't take any more power than that. But the customer needed way more solar, and so what we did was we figured out a way together through some modeling and making sure the costs and the benefits all added up, and it was pretty remarkable. The phrase value stacking gets thrown around a lot, but here's a concrete example of where it actually works. So what we did was we put your battery to keep. From the utility grid's perspective, all they saw at any time was 750 kilowatts. What was happening was the battery was, and then we put like 2 megawatts DC of solar. What the battery was doing was absorbing everything over 750, spreading it out into the afternoon, or saving it till the following morning. And what it was doing was optimizing for demand reduction. There's some TOU arbitrage there by spreading that out. And then by deferring the infrastructure upgrades that would have been accrued if we had wanted to connect 2.2 megawatts DC of solar to the grid, that would have been like a $500,000 upgrade for neutrals, reclosers, and transformers by the utility. So I think, I forget the numbers, it was like a 25% or more IRR and lots more revenue that the customer wanted, but that's going in right now, I think, in Central Valley. Is that, yeah. So that's three value stacks, right? Infrastructure deferral for not having to pay for utility upgrades, demand reduction, and saving the solar for the customer.
Yeah.
We've got another question from the grid. Why don't you read this one, Josh, since you've got the microphone?
Okay, so from Ben Ramos, my question's about residential solar plus storage in San Diego. We can get interval data from SDG&E, then what? What do I do with the data to properly size a storage system for different scenarios? Time of use, game, self-consumption, off-grid, etc. So yeah, so I'll go ahead and take that. I mean, for residential, especially in SDG&E territory, I'm sure many of you know, we work really closely with CALSA as well, and so very recently, SDG&E pushed all their peak rates out into the afternoon, which effectively kills standalone solar. It was really detrimental. So pretty much, yeah. So it's only a flash one. It's just a flash one. So the so you almost have to include storage in every single solar system in San Diego these days, I've noticed. So so what do you do with the interval data? I mean, you do need to do some processing. There's some analysis there. You got to look every 15 minutes. What is the way to optimize the battery's charge? You know, the battery has 3 decisions to make: charge, sit still, or discharge. And you just need to optimize any one of those 3 decisions at a 15-minute level, and see what and that's of course looking in hindsight. You need to look at forecasting into the future if you didn't have that as well. But what you do is use the historical data to put some modeling and simulations together to see how big of a battery you would need to accomplish to maximize revenue, and to do that as cost effectively as possible by selecting the right technology and the right product fit. And so one of the many things that SepiSolar does, and I'm sure you have a team on your staff that does it for your product, we do it across all products and all technologies at SepiSolar. We'll take that interval data, we'll process it, and we'll optimize it for revenue. And all of this is very locationally contingent. You know, every region of the planet has different incentives, like ITC. Is it outside of U.S. where there is no ITC? Is there an SCHIP rebate program? Is it Massachusetts smart? Is it Hawaii or whatever? Whatever the use case is, we'll look at those specific factors and make sure that we're fitting a battery and the right technology for the application to maximize revenue. And it is not unfortunately, it's not a trivial task. It does require some if you will, financial engineering. You need to understand not just kilowatt hours and kilowatts, but dollars and cents, and how you you know, fit all that together to make it right by the customer. Question from the audience.
Question from the audience. Sorry, web guys. And girls.
What kind of modeling software do you use? Do you see that all internally? And what do you recommend for people starting to explore it?
Good question. The question for those of you on the phone or on the web was, what kind of modeling software do we use, and how do you get to those conclusions, or do we recommend anything? So at SepiSolar, having done these so many times, we've actually developed a lot of proprietary in-house tools for ourselves that have proven pretty successful, and they work really well. However, you always want to make sure that whatever you propose on the front end will actually follow a string of events all the way down to the actual real-time operations and controls and the controller and EMS that will operate into the field. So there are EMS providers and control providers. I don't see any here today at the show, but you've probably heard of companies like Jelly, IHI, and Avedis. So there are companies out there that provide those tools. Some of them provide estimation tools. Some of them provide the real-time operations and controls and all together, everything, as well as some performance guarantees. What I like about what we do is just we're not tied to any particular product, and we're also a lot of the challenges I found when we started to use those tools was sometimes they're very specific. Like there's a tool dedicated to demand reduction, but it can't do TOU arbitrage, and it doesn't take blow batteries or flywheels into account. It doesn't do infrastructure deferral. And then there's another tool that maybe does demand reduction and self-consumption and TOU arbitrage, but it doesn't. But it only looks at lithium and maybe one or two other technologies. So I've found personally in my experience using publicly available tools that there are some gaps, and there's no one tool that fits all, one size fits all. So that's part of the bridging and gap filling that SepiSolar is doing, is to try to, any of these custom one-offs or anything that doesn't perfectly fit the mold that somebody put out on the web, we can do that with some smart brains and good software.
Anything to add to that, Matt?
Yeah, just 2 points. We'll see if I get to the second one. The first one being, it's a really good question, because I think one of the things that's often overlooked with storage is that there's a as compared with solar, there's a big gap in terms of the amount of control and operation that you need to have over batteries once they're installed in the field. There's a dispatch decision that has to be made, right? After you've installed a solar array, it's there and it generates power. After you've installed a battery, the hard work starts, and you need to have some sort of software that is sitting there monitoring either your site characteristics or sort of the characteristics of whatever market you're trying to sell into, or the characteristics of the equipment that you're trying to run, and is actively making decisions on whether to dispatch the battery. And picking the right analytical software and picking the right platform to sort of do a lot of that, upfront work is an absolutely critical first step to making sure the battery is really going to do what you want in the long run.
Okay. Anything from the web right now? Oh, no, we got another live one from the audience.
I have a question. I'm Jennifer. So I'm noticing here at Intersolar, there's a lot of new battery companies out there. I'm wondering what you can do when you're evaluating the technology. You're aware of what they need to provide to you for the done.
One of the question. Oh, sorry. The question is, what are some of the questions that we ask when evaluating new battery technologies? Get that right? Okay. One of my favorite, because I'm an engineer, one of my favorite expressions is, "In God we trust, all others bring data." And for battery data, the only thing that I think matters is data that shows performance in a commercial application at scale in the field. And until you've reached that barrier, I can show you hundreds of ways that you can manipulate battery data to show you things that aren't really true. And it's because they are hugely multi-variable problems, right? You can adjust capacity and power and efficiency and all this kind of stuff, and applications and depth of discharge and all these kinds of things to really show whatever you want. But it's when you see the performance of one of these things actually making someone money and actually doing that in real operation at a size that is commercially viable that I think is kind of the barrier to really accepting a lot of the sort of claims that are made.
Yeah. Yeah, I'll just add, being an independent engineering firm and being hired to go in and kick the tires, look under the hood, and do the due diligence work, it is very difficult because there is a lot of what I would call spec gaming, right, where you can put on the spec sheet, this is a 100 kilowatt hour battery, 100% depth of discharge, and you see that it's a lithium battery. And you're like, well, I know 100% depth of discharge for lithium chemistry based on all the technical information and white papers and scientific journals, peer reviewed, that are out there. That's no way possible. And then what we found is when you take off the enclosure, there's an OEM and there's some specifications and part numbers, and you can do some research, and you're like, oh, okay, so it's actually something like an 80% depth of discharge battery. They just don't show it to you on the spec sheet. So that makes a little more sense, and now the dots can connect, and we go on to the next question. So I don't know, some of the questions that I start off with in a technical due diligence process is, first let's look at it. What's included? Just inclusions and exclusions. It's kind of simple, like people throw around dollar per kilowatt hour all the time, but what's in the numerator? Dollars of what? Is this for the cells? Is this for the pack, including BMS or not, including fire suppression, including the enclosure, thermal management, and all the rest, installation? So just figuring out what is in that box. What is there? What are we talking about? That's a logical, kind of a no-brainer first step, but you'd be surprised how much you can run into just in that first step. And then in the denominator, dollar per kilowatt hour. In the denominator, what's a kilowatt hour? Like I just mentioned, is it corrected for depth of discharge? What is the depth of discharge? Do we just take your word on the spec sheet, or do we actually look into this? And then, going into the field and actually testing it, and then testing it over time. I mean, SepiSolar, we're engaged with Nextracker, and one of the coolest things that this has done is this RFP we published that SepiSolar drafted called Decapitate the Duct was precisely to attack this problem. And Avalon has participated in it. Several flow battery companies have participated in lithium companies, and we have Amber Kinetics, Flywheels jumping in as well. It's really exciting. All we're doing is asking a very simple question. We're asking two questions really. One, can you hit this demand profile? And two, who can do it cheaper, better, with less degradation, and perform, et cetera, over time. And so we're just stacking up these batteries side by side across the technology, testing them to the same application, and just seeing which costs more, and which degrades faster, and which doesn't perform as well, and et cetera, et cetera. And at least in Nextracker's case, they ended up settling on a lithium product good for certain lithium applications called Nextracker Drive, and then a flow, actually your battery, for the what they're calling Nextracker Flow for the flow battery applications. So data speaks.
All right. We've got another one from the web. This is from Paul again. Where are we on the energy storage adoption curve, utility versus DG projections? Anybody?
I can answer that, but unfortunately I can't answer that. There was an interesting talk yesterday that I attended up at the conference, and basically what the guy put up there is some of GreenTech Media's projections for the amount of storage projects that were going to be installed in 2018. And that has been met by the number of storage procurements announced in the last 6 weeks. So, I think that what we're going to see is that, the business models around this industry are really starting to be reasonably well understood, or starting to be standardized. And once that happens, the next step is going to be standardization around some of the financing structures that go with it. And once we have those two things in place, you're going to see a massive uptake of these technologies. So, I mean, to answer your question, I think we're really down at the bottom of that adoption curve. It's really just starting to take off.
Yeah, I've got a question for both of you, and that is, when will batteries be, of all flavors, cheap enough and available enough to replace base power with solar or wind and all those other things? And when do you project that we'll be able to, we'll have a choice between a regular baseload natural gas plant and a solar plus or wind plus?
I think we have that choice now. I don't think that choice is going to exist for very long, because within 2 to 3 years we're going to see dispatchable renewable generated electricity plus batteries available for less dollars per megawatt hour than any conventional source of generation.
And that's that.
Yeah, I would agree. I mean, based on the costs and that from the utility and as well as the cost curves we're seeing across technologies, really, for storage and for solar. I mean, those are, of course, are variables, as we all painfully know. But it is actually, the LCOEs and having a long duration, reliable battery that doesn't degrade, that is charging from solar, and even when you include things like ITC, so you restrict the battery to only charge from a renewable source. Today, with our existing policies, with existing structures, and with the technologies, I see that. Yeah, I do. We've seen a little bit of that, and actually more so in developing countries, I would say. So forget ITC. Actually, we've seen in like Southeast Asian areas where people are putting solar and long-duration storage together, sometimes with or without the solar gas generation, because it is cheaper than the alternative.
All right. That's really all we have time for. If you've missed any of this, we have recorded this. It will be on our blog, and if you actually signed up for it on the web, then you'll get it emailed to you, and you can watch it again or share it with your friends. This has been Ask SepiSolar Anything, and we do this every month with a different topic, and sometimes we have a special guest, and so we'd like to thank our special guest this week, Matt Harper from Avalon.
And thanks very much for inviting me. It's been a pleasure to be here.
All right. Thanks, everybody, for coming.